In this lesson, we're going to be looking at one last type of reaction known as oxidation-reduction reactions. So these are often referred to as redox reactions for short, because oxidation reduction is a bit of a mouthful. So what these are is these are electron transfer reactions. So in a lot of reactions, in those that are not oxidation-reduction reactions, atoms move around and connect to, and disconnect from different things and rearrange themselves, but they keep the same number of electrons with them. In oxidation-reduction reactions, that is not true. That in the rearrangements that are occurring, atoms are actually gaining and losing electrons. So whether something gains or loses is referred to as either reduction or oxidation, respectively. And these two things always happen together. So oxidation, specifically, we think about it by itself, is a loss of electrons. And reduction is a gain of electrons. And these two things must always happen together because your electrons need somewhere to go. Electrons want to be attached to an atom. They do not want to be floating around by themselves, generally speaking. So if one thing loses electrons, they're going to go somewhere and be gained by something else. So when something is oxidized, something else is being reduced, and hence we have oxidation reduction or redox for short, because these two things always have to happen together. So part of why we want to talk about these and recognize that these are a thing that happens is that we need to, when we are balancing reactions, we need to make sure that all of our electrons are accounted for. And in reactions that are not redox reactions, we just don't even need to think about that because it happens by itself. If all of your electrons are moving with the atom they started with, when you balance your reaction just by counting how many of each type of atom there are, the electrons are going to balance themselves. You don't need to think about it separately. But for reactions that are redox reactions, that's not always going to be the case. So for example, if we look at something like this, so let's say we have silver ion reacting with copper to produce silver and a copper 2+ ion. So at first glance, you might say, oh, that's balanced. There's one silver on each side and there's one copper on each side, and that is accurate. But this is actually not balanced because the total charge on both sides is not the same. And what that means is that we misplaced an electron somewhere along the line, one or more electrons. So over here, the total charge on all of my reactants is +1. I have a +1 on the silver and 0 on the copper. On the right side, I have 0 on the silver and +2 on the copper. So the total charge on the right is +2. So we can see that they're not the same. In a balanced reaction, they must be the same. The total charge on the reactants must equal the total charge on the products. So now we need to think about more than just how many atoms are on each side when we're balancing things. We do still need to balance that as well, but we also need to take charge into account. So for a reaction, for a redox reaction as simple as this one, it's relatively straightforward to see how we can just add coefficients to make these charges equal. But I want to show you a method that can be used for more complicated reactions that will help you with balancing redox reactions in a more general sense. So for this one, you can probably look at it and see what the answer is going to be. For the balancing, for the coefficients we need to add to balance this. But a method that is often useful for more complicated reactions is that we can think about the oxidation reaction and the reduction reaction separately. They won't actually happen separately, but we can think about them as separate things. And we call this type of process a half reaction. Since it can't really happen the way we are writing it, it is just half of the redox process. So if we want to break this process down into half reactions, we want to think about what is this reactant turning into. So silver is going to stay silver. The only thing that is changing about it is its charge. So the silver ion, silver +1 ion, is going to become the silver with no charge, and the copper is going to become the copper 2. So at this point, we can think about what must be happening in terms of electrons in order for these charges to change the way that they are changing. Remember that electrons are negatively charged. So in order for something to go from a +1 charge to 0 charge, it must be gaining an electron. Cations have fewer electrons than neutrally charged atoms. So this silver must be gaining an electron, meaning that that silver plus ion is being reduced. So we would call this our reduction half reaction. Because this silver plus is gaining an electron to become silver 0. In the second one, we have copper 0 becoming copper 2 plus. In order for that to happen, this copper must have lost not 1 but 2 electrons in order to end up with a positive 2 charge. So those were given off and separated from that copper atom. So we now have a copper 2 plus ion and 2 electrons that have been separated from that. And since that copper lost electrons, we would call this our oxidation half reaction. So to balance this, what we need to do, so to balance our overall reaction, we need to make the number of electrons lost in our oxidation equal. So we need to make electrons lost, need electrons lost to be equal to electrons gained. So we can see when all of our coefficients from our reaction are 1. We had 1 silver, 1 copper, 1 copper. We are gaining 1 electron in the reduction, but we're giving off 2. So in order to balance our overall reaction, we need to make those numbers equal. And we can do that by multiplying either or both of our half reactions, however is necessary, by some factor in order to make those numbers be equal. So in this case, we would need to multiply our first half reaction through by 2, and note that we do have to multiply every single thing in that half reaction by 2 in order to keep the half reaction balanced. And then when we put this back together, my electrons lost and my electrons gained are going to cancel each other out. And my overall reaction, we can see now has 2 silver on each side. So I will have 2 Ag plus a copper, forming 2 Ag and copper 2 plus. So all I've done here is taken everything on the left side of my reaction, except for the electrons, and put it on the left side of my overall reaction. Everything on the right side of both of my half reactions, except for the electrons, goes on the right side of my overall reaction. And I now have a balanced oxidation-reduction reaction, where the total charge on the left is +2. I have 2 ions, each with a +1 charge, giving me a total of +2 over here. And then I still have this +2, just one of them, giving me a total of +2 over here. So again, for a reaction this simple, this method probably isn't really necessary, but for more complicated reactions, this method of splitting this apart into half reactions, making your numbers of electrons equal, and then adding your reactions back together can really, really be helpful in certain situations. And I will expect you to be able to look at a half reaction and balance it, as well as sort of taking the beginnings of an overall reaction and identify what would the oxidation half reaction look like and what would the reduction half reaction look like as well.